All right, so let's suppose you just poured yourself a cup of coffee, nice, hot, freshly brewed cup of coffee that is at 95 degrees Celsius. And then you pour it out and it's in a room where the temperature is 20 degrees Celsius. So if you set their coffee down, it's going to cool, right? It's going to cool off. And first question you want to think about is, well, how is it going to cool? When do you think the coffee cools the most quickly? Well, the coffee cools most quickly when the temperature difference is the greatest. Okay, so when you first pour that cup of coffee, it's going to cool down fairly quickly, but then eventually it's going to over the long term it's going to reach the temperature of the room, right? You're assuming that the room is a big enough heat sink that it's not going to change the temperature of the room, right? The coffee is kind of small compared to the room, so the room isn't really going to change temperature because of the coffee, but the coffee is going to cool off, and eventually it'll be at room temperature, and it's not going to go any lower than room temperature. So it's going to kind of approach the room temperature asymptotically. All right, so Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. All right, so here we have the word proportional again. So we're dealing with proportional relationships here. Provided the temperature difference is not too large. Okay, so it's just, maybe if you took it out on a really, really, you took your coffee outside on a really, really cold day, obviously you have the issue of a state change. So, it's going to go, a lot more of that coffee is going to evaporate directly and not just cool down and stay in a liquid state. So we're asked to write a differential equation that expresses Newton's law of cooling for this particular situation. Okay, and so let's think about what it says. So it says that the rate of cooling. All right, so that's basically the rate of temperature change. So I'm going to write dt, capital T representing temperature, dt, where lowercase t represents time. Okay, so I know I'm using two t's here, but a lot of times you see that. Capital T represents temperature and lowercase t represents time. Okay, and that's equal to we need some constant of proportionality, right? Because it's a proportional relationship. And if we think about it, if we're talking about cooling, the rate of change of temperature over time is going to be negative, right? Because the temperature is going to decrease. So I'm just going to go ahead and put in a negative K. Okay, so then if we're talking about cooling, then K would be positive. But the negative then represents the fact that if it's cooling, the temperature is going down. So dt, the rate of change of temperature over time, is negative. Okay, and it's proportional to the difference between the object and its surroundings, right? So let's say the temperature of the object is T and the temperature of the surroundings is T sub A. So I'm going to use T sub A to represent the ambient temperature. So T sub A, maybe I should define that, is the ambient temperature. Okay, so that's just the temperature of the surroundings. Okay, and then K is just some constant of proportionality. And we just threw in a negative because we know we're dealing with cooling. All right, so there's a differential equation for you. And the part C is asking us to make a rough sketch of what we think the solution will look like. Now, I think if I didn't, so what is the initial condition? Well, for this particular problem, the temperature of the coffee at T equals 0 is 95 degrees. So we could also say that T0 is equal to 95 degrees Celsius at T equals 0. Okay, so that's our initial condition. All right, so let's draw a little sketch of what we think this is going to look like. All right, so it's hot coffee. So we're starting out. This is our temperature and this is time. And let's just draw our ambient temperature. So this dotted line represents the ambient temperature, TA. So it starts out hot, and then it's going to cool, but the rate of change of cooling gets more and gets less negative, right? It's negative, but it slows down as you're approaching the ambient temperature. So that's probably what it's going to look like. All right, and then in part D, we're asked to actually solve Newton's law of cooling. All right, so let's do that. Got to give ourselves plenty of room. All right, well, let's go back up and look at this equation. All right, it looks like we ought to be able to separate those variables pretty easily because we don't have any lowercase t for time. It's all in terms of the uppercase T temperature. So if we separate the variables, we're going to get 1 over T minus T sub A dt, capital T. It's kind of a little bit confusing with lowercase and uppercase t, but I think it's not bad. All right, and then we're going to leave the minus k over on the other side, and we have dt, and then we're going to integrate both sides. All right, well, this is not too bad. So over here I get the natural log of T minus T sub A. T sub A is just a constant, right? It's just our ambient temperature. And on the right-hand side, I'm going to get minus K T plus C. All right, so this looks like something we've done before, right? So we get T minus T sub A, absolute value of that, is equal to e to the minus K T plus C. And then we can write this as T minus T sub A is equal to, I'm going to make e to the c just to be a constant, and I get, right, because this is essentially e to the c times e to the minus k. So I'm going to get a, kt, right, a e to the minus kt, okay. And then I want to solve for t, so I'm just going to move that constant ta over, so I get t is equal to a e to the minus k t plus t sub a. All right, so we got a lot of constants in there. We've got a, we've got k, and we got t sub a. So we already know what t sub a is. That's what we said was the ambient temperature. But let's say that let's let if t is equal to t0 at t equals 0, okay, then we can solve for that constant a. So what I'm going to get is, I'm just going to plug in t0 for t, and then the time t is 0. So I get what? I get t0 is equal to a e to the 0 plus t sub a. Okay, and I want to solve for a, so I'm just going to subtract t sub a, and I'll get a is equal to t0 minus t sub a, which is basically the temperature difference between the initial temperature of the coffee and the ambient temperature. All right, so now that we know a, we can actually solve this and get a solution. So we're just going to put this t0 minus ta in for a. So we get t0 minus ta, okay, that's times e to the minus k t plus t sub a. All right, so there's our general solution to that differential equation. All right, so now this is just a general solution. Now, if we know our original problem said that the coffee was 95 degrees, so that's our T0 is equal to 95 degrees C, and our ambient temperature T sub A is equal to 20 degrees C, and so we can use that to solve or to find an equation for this particular situation. So our equation, if we're looking for the equation for this particular situation, we essentially have 95 minus 20, right? T0 minus TA, e to the minus kt plus 20. Okay, and I could simplify that a little bit by taking 95 minus 20, so I get 75 e to the minus kt plus 20. All right. Now you notice we still have a constant in there, right? We still have this k constant. And so we really would not be able to solve this unless we know this k value, okay? And you know, if you take thermodynamics or heat transfer, or you know, some physics that involves heat, you'll learn that this k depends on the heat transfer coefficient and the surface area. So but we could figure that out, you know, if we took the temperature at, say, 2 different points. You know, we have the initial temperature, and then if we knew that after, you know, 2 minutes the coffee was at a different temperature, if we knew what that temperature was, then we could actually find k. But with the information we're giving in this problem, we don't really know. We can't actually solve anything. We can't find what the temperature is at any given time unless we know one more piece of information. So so that's all we can do on this problem. But we got a general formula for Newton's law of cooling down here now, and it might come in handy in some of the discussion questions of the homework. So that's all I have for the examples, and you are... What? Nope. Oh, wait. Nope. We're not done. It's got one more topic to cover, don't I? And one more example and another topic, which is very important. So stay tuned. I'll see you in the next video.